Off the coast of Vancouver Island, the ocean floor just dropped 5 kilometers straight down. You felt the shake all the way in Vancouver, but what scientists found underneath is stranger than the quake itself. Deep below the waves, 2 giant slabs of earth are grinding apart, breaking off piece by piece like train cars snapping loose. Ahead, we travel to a fault that turns silent right before it breaks. A forest still standing underwater from Canada's last mega-quake, and a hidden crack where 3 tectonic plates fight for the same ground. If stories like this pull you in, tap like and subscribe. It truly helps the channel grow. Now brace yourself. We begin. On the night of July 20th, 2026, the coast of British Columbia jolted awake. 11:41 at night. Most people were asleep, phones charging, houses quiet. Then the ground moved. A magnitude 5.6 earthquake tore through the sea floor west of Vancouver Island. It struck about 6 miles under the ocean, roughly 136 miles southwest of a small town called Port Hardy at the island's northern tip. The shaking rolled east. People felt it in Campbell River. They felt it in Port Alberni. They felt it in Metro Vancouver, 280 miles away, where office towers swayed just enough for people to look up from their phones. No warning came first. No siren. No alert on your screen a full minute early. Just a sudden jolt, then a second, smaller quake minutes later, as if the earth were clearing its throat before it spoke again. Earthquakes Canada checked their instruments within minutes. No tsunami danger, they said. No reports of serious damage. For most people watching the news that night, the story ended there. A shake, a headline, then silence. But for a small group of scientists watching seismic stations up and down the coast, the story was only getting started. This quake struck along one of the most closely watched stretches of ocean floor on the entire planet, a place where 2 enormous slabs of the Earth's crust have been locked in a silent, centuries-long struggle. Picture the ocean floor near Vancouver Island less like solid ground and more like a rug lying on top of a treadmill. Somewhere beneath your feet, that treadmill never stops moving. It has been sliding for millions of years, dragging rock toward the coast, then downward, deep beneath the continent. Most of the time, you would never know it. The motion is slower than your fingernails grow, a few inches a year, if that. Then, every so often, the rug catches. Friction locks the 2 surfaces together, and pressure builds in the rock the way pressure builds in a bent stick. Something has to give. When it finally does, the ground doesn't creep. It snaps. That snap is what people felt on July 20th. A small release in the grand scheme of things. A whisper compared to what this same stretch of coastline is capable of producing. Here is the part that should make you sit up. 2 weeks earlier, a separate team of scientists had quietly published something strange about this exact patch of ocean floor. Using sound waves fired from a research ship, they had photographed a hidden crack running deep beneath the seabed, showing the ocean floor itself splitting apart in a way nobody had ever captured this clearly before. They weren't looking for it because of the earthquake. The earthquake and the discovery arrived within weeks of each other by coincidence, 2 signals from the same restless patch of the planet. But together, they turned a routine tremor into something far bigger. A window into a hidden process happening under the waves, one most people will never see, and one scientists are only now beginning to understand. To understand what that window revealed, you first need to understand exactly what kind of boundary Vancouver Island is sitting on top of. It has a name most Canadians have never heard, and it stretches for hundreds of miles down the coast, quietly shaping earthquakes, mountains, and volcanoes, long before anyone thought to give it a name at all. A magnitude 5.6 earthquake. Sounds small when you say it out loud. 5.6. It barely registers as a number. But numbers on the earthquake scale do not behave the way normal numbers do. Picture a set of stairs. Each step up does not add a little more power. It multiplies it. Move up 1 full step on the scale, say from magnitude 4 to magnitude 5, and the shaking on the ground gets about 10 times stronger. The actual energy released, the raw force punching through solid rock, jumps by roughly 30 times. Climb another step to magnitude 6, and you multiply all of that again. So a magnitude 5.6 earthquake is not a gentle wobble. It releases roughly the same energy as several hundred tons of explosives going off at once, deep underground, spread out over several seconds instead of a single blast. That is enough force to rattle windows, sway tall buildings, and send anyone standing near the coast rushing for a doorway. Compare it to something you already know. A city bus weighs around 10 tons. The energy behind this one quake could have lifted tens of thousands of buses off the ground at the exact same moment. Now stretch that force out along a fault line under the ocean, and you start to understand why a quake that struck 136 miles offshore could still be felt swaying towers in a city hundreds of miles away. Here is the part that catches people off guard. Magnitude 5.6 is not close to the biggest earthquake this coastline can produce. Scientists sort earthquakes the way you might sort storms. A magnitude 5 sits somewhere near a strong summer squall, unpleasant, occasionally damaging but survivable, forgettable within a week. A magnitude 8 or 9 earthquake belongs in an entirely different class. Think Category 5 hurricane, except the hurricane is made of solid rock, and it arrives with almost no warning at all. That comparison matters because the fault that produced this quake sits close to the same system capable of producing that Category 5 version. Scientists have measured it. They know its history. They know roughly what it did the last time it truly let go. So why did July 20th only produce a moderate shake and not something catastrophic? Part of the answer is not really about the earthquake at all. It is about where the earthquake struck, under 6 miles of solid rock, and underneath every bit of that, an entire ocean. That detail might sound small. It is not. It is the difference between an earthquake that flattens buildings and one that barely makes the evening news. Duration tells part of the story too. The July quake likely lasted only a handful of seconds down on the seafloor itself. By the time that shaking travelled through more than 100 miles of rock and water and finally reached buildings on shore, it had stretched out and softened, arriving as a gentle sway rather than a sharp jolt. A true megaquake behaves nothing like that. Some of the largest earthquakes ever measured have kept the ground shaking continuously for 3 or 4 full minutes, long enough for people inside tall buildings to wonder whether the shaking will ever stop. That single detail, how long the ground keeps moving, points straight toward the real reason scientists have been staring at this stretch of Pacific coastline for years, waiting to see what happens next. Location decides almost everything about how dangerous an earthquake turns out to be. Not the number on the scale, not even how deep it strikes. Where it strikes, relative to you, decides whether an earthquake becomes a headline or becomes a disaster. The July quake hit about 6 miles beneath the seafloor, then travelled upward and outward through more than 100 miles of open water before it ever reached a coastline. Compare that to an earthquake striking directly under a city, shallow, close, with nothing standing between the shaking rock and the foundations of every building above it. Distance and depth both act like a cushion. They do not erase the danger. They spread it out, softening the blow by the time it reaches anyone standing on solid ground. Water adds a second layer of complexity. An earthquake striking on land shakes buildings directly. An earthquake striking under the ocean can do something far stranger. It can shove an entire column of seawater upward, all at once, and send that motion racing outward as a wave. A tsunami is born when the seafloor lurches up or down, like the bottom of a bathtub suddenly tilting, shoving the water above it outward as a wave. So why didn't July 20th trigger a tsunami warning? The answer comes down to the type of motion involved. Picture 2 sheets of sandpaper, slide them past each other sideways, and you get friction, noise, plenty of energy, but the surfaces stay level. Now instead, imagine one sheet lurching straight down while the other stays put. That vertical drop is what shoves water out of the way and builds a wave. The July earthquake involved mostly sideways motion, plates grinding past each other instead of one plate suddenly dropping beneath the other. Scientists figured this out almost immediately, using a diagram built from how the shaking waves radiated outward from the quake in every direction. That diagram works a little like reading footprints at a crime scene, showing investigators exactly which way the ground moved even though nobody was there to see it happen. Earthquakes Canada confirmed there was no tsunami risk within minutes, and the ocean stayed calm. A different kind of quake striking along a different kind of fault nearby would tell an entirely different story. That nearby fault is the one worth worrying about. It runs along the true subduction boundary, the place where one entire slab of ocean floor dives underneath the edge of the continent instead of sliding past it. When that boundary finally breaks, the motion is not sideways. It is a sudden, massive vertical drop, capable of displacing enough seawater to send waves taller than a house, racing towards shore within minutes. Scientists know this because it has already happened here before, more than once. They also know that quakes like the one on July 20th, smaller, sideways, survivable, tend to cluster near the edges of these larger, more dangerous faults. It is part of why researchers treat every tremor along this coast the way a nurse treats a change in a patient's heartbeat. Individually, it might mean nothing. Set against the right background, it might mean everything. To understand what that dangerous background actually looks like, you have to go looking for it in a place few people ever think about, a map of the ocean floor itself, where an invisible boundary has been quietly shaping this entire coastline for millions of years, long before anyone built a single bridge or highway on top of it. Most Canadians have never heard the name Cascadia. That's strange, considering it might be the single most important geological feature on the entire west coast of North America. Cascadia is not a place on a road map. You will not find road signs pointing toward it, no city named after it, no border crossing marking where it begins. Cascadia is a subduction zone, a place deep underwater where one enormous piece of the Earth's crust is sliding beneath another. It runs for about 700 miles, stretching from Cape Mendocino in Northern California, up past the coasts of Oregon and Washington, all the way to the northern tip of Vancouver Island in British Columbia. Here is the simplest way to picture it. Take two moving walkways at an airport, the kind that carry you forward while you stand still. Now imagine lining two of them up end to end, except one is built slightly lower than the other. Where they meet, the lower one slides underneath the higher one instead of stopping. That is roughly what is happening beneath the Pacific Ocean, except instead of rubber and metal, it is solid rock, moving at a pace slower than your fingernails grow, and the walkway sliding under the coast is a slab of ocean floor thousands of feet thick. The name itself comes from the Cascade Mountain Range running along the same stretch of coastline, a chain of volcanic peaks most people recognize even if they have never connected them to anything happening underground. Driving the full length of Cascadia by car from Northern California to the northern tip of Vancouver Island would take longer than an entire day behind the wheel without stopping, a distance most people never think to measure in one continuous line. The reason most people have never heard of Cascadia comes down to timing. This entire boundary produces its largest, most violent earthquakes only once every few hundred years, sometimes longer. Compare that to a fault line that ruptures every few decades, constantly reminding nearby cities that it exists. Cascadia goes quiet for so long that entire generations grow up, live and die, without ever feeling its full power. That silence has a cost. It lets people build cities, bridges and pipelines directly on top of a hazard most residents never learned to fear. Every quake felt along this coast, including the one on July 20th, traces back in some way to this same restless boundary. Sometimes the connection is direct, rock grinding along the main subduction fault itself. Other times, like with the July quake, the connection is more like a distant cousin, a smaller fault nearby, shaped and stressed by the same enormous forces bending the crust around it. Scientists divide Cascadia into sections, the same way you might divide a long highway into different stretches with different speed limits and different histories of accidents. The northern end, closest to Vancouver Island, behaves differently than the southern end near California. It bends differently, it stores stress differently, and as researchers recently discovered, it might even be starting to come apart differently than anywhere else along the entire boundary. That difference starts with two names most people have never spoken out loud. Two slabs of ocean floor sliding beneath the continent side by side, close enough to interact, different enough to behave like total strangers. One of them is the main engine driving this entire subduction zone. The other is smaller, stranger, and sits at the exact center of the mystery scientists are racing to understand. Meet the Juan de Fuca Plate, the slab of ocean floor doing most of the heavy lifting beneath Cascadia. It is not one of the giant plates you might have learned about in school. nothing like the massive Pacific or North American plates that stretch across thousands of miles. The Juan de Fuca plate is small by comparison, almost a leftover piece, squeezed between larger neighbours on every side. Small does not mean harmless. This plate is being born, pushed and destroyed all within the same narrow stretch of ocean. Far offshore, molten rock rises up from cracks in the seafloor, cools and hardens into brand new crust, adding fresh material to the plate's western edge. That same plate then creeps eastward, toward the coast, at a pace of about 1.5 inches every year. Stretch out your hand and picture your fingernail growing. That is roughly the same speed carrying an entire slab of ocean floor toward the edge of a continent. When the Juan de Fuca plate finally reaches the coast, it does not stop. It cannot stop. The North American continent is thicker, lighter, and sits higher, so the heavier ocean slab has nowhere to go but down. It dives beneath the coastline at a shallow angle, sliding deeper and deeper into the earth, carrying seawater, mud, and rock down with it like a conveyor belt feeding material into a furnace. That furnace is real. Heat and pressure inside it truly melt rock, deep beneath the mountains above. As the plate sinks deeper, heat and pressure begin cooking the rock and water trapped inside it. Eventually, some of that material melts, and the melted rock rises back up through cracks in the crust above. That process built the volcanoes running down the spine of the Pacific Northwest, including Mount St. Helens, the volcano that erupted so violently in 1980. Every one of those mountains exists because of the same slow collision responsible for the earthquake felt off Vancouver Island in July. Here is where the danger comes from. As the Juan de Fuca plate dives beneath the coast, friction locks the two surfaces together along the upper section of the boundary, the part closest to shore. The plate wants to keep sliding. The friction refuses to let it, so instead of smooth, steady motion, the rock bends, storing energy the way a diving board stores energy when you press down on the end of it. That stored energy does not disappear. It waits, sometimes for decades, sometimes for centuries. Scientists call this a locked zone, and the entire Pacific Northwest is sitting directly on top of one right now. Researchers track this slow build-up using networks of extremely sensitive GPS stations bolted onto solid rock along the coast, instruments precise enough to detect ground movement measured in fractions of an inch. Over years of monitoring, those stations show the coastline itself creeping slightly inland, squeezed by the locked plate beneath it, the same way a diving board tip drifts downward the longer you keep your weight pressed on the end of it. But the Juan de Fuca plate does not act alone. Squeezed into the northern end of this same subduction zone, close to where the July earthquake struck, sits a second, smaller slab of ocean floor. Stranger in shape, more chaotic in its movement, and now at the very center of a discovery that has scientists rethinking what a dying subduction zone actually looks like. The Explorer plate might be the strangest piece of crust on the entire west coast of North America. Most tectonic plates behave predictably, moving in one steady direction for millions of years at a time. The Explorer plate does not follow that rule. It sits wedged into the very northern tip of the Cascadia subduction zone, squeezed between three much larger neighbours, the Pacific plate to the west, the North American plate to the east, and its own larger cousin, the Juan de Fuca plate to the south. Being surrounded on every side by bigger, more powerful plates is a little like being the smallest kid at a crowded table, pushed and jostled from every direction at once, with barely enough room to move in a straight line. That crowding shows up clearly in how the Explorer plate behaves. Instead of diving smoothly beneath the coast the way its larger neighbour does, parts of the Explorer plate barely move at all, locked in place by the pressure of the plates surrounding it. Other parts twist and rotate, dragged along by forces pulling in different directions. Geologists studying this region have long described it as one of the most complicated tectonic puzzles on the planet, a place where the usual rules of plate motion start to break down. Here is a comparison that might help. Imagine three cars trying to merge into the exact same lane on a highway at the exact same moment, each one pushing and nudging the others out of position. Nobody involved is moving in a smooth, predictable line anymore. That chaos, frozen in slow motion over millions of years instead of a few seconds, is roughly what the Explorer plate has been dealing with since it formed. Places where three separate plates meet in one spot carry a special name in geology, a triple junction. They rank among the most complicated, least predictable corners on the entire planet, because the usual rules that describe how two plates interact simply stop applying cleanly once a third plate joins the fight. Scientists have studied triple junctions in other parts of the world for decades, and nearly every one of them turns out to behave differently from the others, shaped by whatever unique mix of forces happens to be squeezing that particular corner of the Earth. This crowded, chaotic corner of the Earth turns out to matter enormously for the story of the July earthquake. The quake itself struck close to the boundary between the Explorer Plate and its larger neighbour, along a fracture zone scientists call the Nootka Fault, one of the few places on the planet where three separate plates meet in the same tangled knot at once. Scientists studying this region recently used a research ship to look beneath the seafloor here in unprecedented detail, hoping to finally understand how these crowded, competing plates interact deep underground. What they found went far beyond anything they expected, direct evidence that the ocean floor itself, in this exact stretch of ocean, is coming apart. To see how they found it, you have to go back to the ship that made the discovery possible, and the strange technique researchers used to photograph something no human eye will ever see directly. A picture of the Earth's insides, built entirely out of sound. Nobody can dig a hole 3 miles straight down through solid rock and ocean floor just to take a photograph. So scientists had to find another way to see what lies beneath the seabed off Vancouver Island. Their solution borrows an idea straight out of a hospital room. Doctors use ultrasound to see inside a patient's body without ever making a cut. A machine sends sound waves into the body, and those waves bounce differently off different types of tissue, muscle, bone, fluid, each one reflecting sound in its own particular way. A computer reads those reflections and turns them into an image. Geologists use almost the exact same trick, scaled up to the size of an ocean. A research ship tows an airgun behind it, a device that fires a burst of compressed air into the water at regular intervals, sending a sharp pulse of sound down through the ocean and into the rock below. That sound travels downward, bounces off different layers of rock buried underground, and reflects back up toward the surface. To catch those returning echoes, the ship also drags something almost impossible to picture at first. A cable more than 9 miles long, packed with thousands of underwater microphones, stretched out behind the vessel like an enormous fishing line built entirely out of listening devices. Every microphone records the exact moment the sound waves bounce back, and every recording adds one more piece to a growing underground picture. Layer enough of these recordings together, from thousands of individual sound pulses fired along the same stretch of ocean, and a detailed cross-section starts to emerge. Not a blurry shadow, a sharp, layered image of buried rock, faults, and fractures, built entirely from sound instead of light. This technique is called seismic reflection imaging, and it is the closest thing geologists have to an ultrasound of the entire planet. It has been used for decades to search for oil and gas hidden underground, where energy companies needed sharp pictures of buried rock layers before drilling a single well. Only recently have scientists turned that same technology toward a very different goal, mapping one of the most dangerous earthquake zones on the entire west coast of North America in far greater detail than anyone had managed before. Older surveys of this same coastline relied on far fewer instruments, producing blurry, low-resolution images that hinted at buried structure without ever confirming it clearly. The newer survey fired sound pulses again and again along the same stretch of ocean, thousands of times over, layering each new echo on top of the last until faint, uncertain shapes sharpened into something scientists could finally trust. The results do not arrive instantly. A single expedition can generate months, sometimes years of raw data. Far too much for any person to study by eye alone. Teams of researchers spend that time combing through the recordings, layer by layer, searching for patterns hidden inside the noise. In this case, buried inside months of recordings gathered off the coast of Vancouver Island, one particular pattern stopped researchers cold. A pattern nobody had seen mapped this clearly before. Hiding inside a stretch of ocean floor everyone assumed they already understood. A stretch that had already been surveyed, studied, and written about for decades without anyone noticing what was really happening underneath it. The ship responsible for this discovery has a name most people will never hear again after this video ends, so remember it for the next few minutes. It is called the Marcus Langseth, a research vessel built specifically for missions like this one, operated by scientists at Columbia University's Lamont Doherty Earth Observatory in New York. In 2021, a team of researchers loaded that ship with equipment and set out on an expedition called the Cascadia Seismic Imaging Experiment. Their goal sounded simple on paper: map the hidden structure of the Cascadia subduction zone in more detail than anyone ever had, from the coast of Oregon all the way north toward Vancouver Island. Leading that expedition was a scientist named Susan Carbott, a researcher who has spent much of her career studying what lies beneath the world's oceans. She served as chief scientist on board, overseeing a crew firing sound pulses into the water day after day, week after week, gathering the raw recordings that would eventually reveal something nobody expected. Expeditions like this one are not quick trips. Sailing back and forth along hundreds of miles of coastline, towing a cable longer than most bridges, takes weeks of careful, repetitive work. Every pass adds another slice to an enormous underground picture, one thin layer at a time, the same way a doctor might scan a patient section by section to build a complete image of what lies inside. Once the ship returned to port, the real work had barely started. Around 20 scientists from universities across North America spent years afterward combing through the data the expedition produced, searching for patterns buried inside thousands of hours of recordings. Researchers from Louisiana State University, Auburn University, and the University of Texas at Austin joined the effort alongside the original team from New York, each institution contributing its own expertise to a single, shared data set. Among them was a researcher named Brandon Shuck, who led the analysis that eventually connected the dots. The entire expedition had been funded by the National Science Foundation, a government agency that backs scientific research considered valuable enough to support with public money, even when nobody involved knows exactly what the data will eventually reveal. What they were looking for at first was simply a clearer picture of the main subduction boundary, the place where the Pointe de Fuca plate dives beneath the coast. What they found instead, hidden near the northern end of that boundary, close to where the Explorer plate crowds into the picture, was something none of them had gone looking for: a break, a massive fracture, cutting straight through the descending slab of ocean floor, visible clearly enough in the imaging that researchers could trace its shape for dozens of miles. Finding a hidden fault is not unusual work for a geologist. Finding one this large, this clear, and apparently this active is far rarer. The team spent months double-checking their results, comparing the imaging against decades of earthquake records from the same stretch of ocean, making sure what they were seeing was real and not some trick of the data. It was real, and once they confirmed it, the discovery led them somewhere even stranger. Proof that an entire slab of ocean floor right beneath the waves off Vancouver Island had already started falling apart. Picture a slab of rock roughly the size of a small country, sliding steadily beneath the coast of British Columbia for millions of years without interruption. Now picture a section of that same slab suddenly dropping straight down, sinking about 3 miles lower than the rock sitting right beside it. That is exactly what researchers found buried beneath the ocean floor off Vancouver Island. 3 miles does not sound like much written on a page. Stand it up and compare it to something familiar. 3 miles is taller than any mountain in the United Kingdom. It is deep enough to bury the tallest skyscraper on Earth more than 5 times over, stacked one on top of the other, and this entire drop happened along a single continuous fracture, cutting straight through solid rock that had spent millions of years moving as one connected piece. Scientists call this kind of fracture a fault, the same word used to describe the cracks responsible for ordinary earthquakes. What makes this particular fault so unusual goes beyond its size alone. It is where it sits, and what it is doing to an entire slab of ocean floor that geologists assumed was still moving in one piece. Earlier surveys of this coastline had picked up hints of something unusual in this exact area, scattered clues that never quite added up to a full picture. Some older studies noticed odd bends in nearby rock layers. Others noticed unusual clusters of small earthquakes without ever explaining why they clustered there. The new imaging finally connected every one of those separate clues into a single, coherent answer. For years, the standard picture of a subduction zone looked something like a single sheet of rock sliding steadily beneath a continent, bending smoothly, wearing down slowly, staying more or less intact the entire way down. The imaging off Vancouver Island shattered that picture. Instead of one smooth sheet, researchers found a slab actively ripping apart, breaking along internal fractures the same way a cracked windshield splits into separate pieces under enough pressure. This came from a direct photograph, built from sound waves, capturing the fracture exactly as it sits today, buried beneath the seafloor right now, while you listen to this sentence. Researchers published their findings in a scientific journal called Science Advances, sharing the images publicly so other experts around the world could study them, question them, and test them against their own data. That kind of open scrutiny matters enormously in science. A single research team claiming a dramatic discovery means little on its own. A discovery that survives careful examination by outside experts starts to mean a great deal more. So far, the imaging has held up. Other researchers studying the same region have found matching patterns in decades of earthquake records collected along this stretch of coast, evidence that lines up with what the ship's sound waves revealed. Two completely different types of data, gathered through two completely different methods, pointing toward the exact same conclusion. An entire slab of ocean floor sitting directly beneath one of Canada's most populated coastlines is tearing itself apart in real time. This is happening here, now, beneath water most people will never sail across, in a process scientists had never managed to photograph so clearly before. The next question became obvious almost immediately. If a subduction zone can tear like this, quietly, without anyone noticing for millions of years, what does that mean for the earthquakes it produces? Scientists split into two very different answers. An earthquake and a tear might sound like two words for the same thing. They are not, and the difference matters enormously if you live anywhere near this coastline. An earthquake is a release. Stress builds up along a locked fault for years, decades, sometimes centuries, and then it lets go all at once, sending shock waves racing outward in every direction. Once the release happens, the stress resets, and the slow build-up starts again from close to zero. A tear works differently. A tear is closer to a slow, permanent breakup, rock physically separating into two disconnected pieces that will likely never rejoin. Once a section of the Juan de Fuca plate tears completely free, it stops behaving like part of the same connected slab. It becomes its own separate fragment, drifting on its own, following its own path deeper into the earth. Here is why that distinction changes everything about how scientists think about earthquake danger along this coast. Earthquakes happen because rock is still connected, still locked together, still capable of storing and releasing stress. A section of ocean floor that is fully torn away, fully separated from its neighbour, stops producing earthquakes in that exact spot. There is nothing left grinding together. The rock simply drifts. That might sound like good news at first. Less connection, fewer earthquakes right there. Reality is more complicated. A crack does not erase the forces driving the whole system. It simply redirects them, the same way rerouting one lane of highway traffic does not remove the cars from the road. It just sends them somewhere else, sometimes onto streets never designed to handle that kind of load. Tearing does not lower the overall danger along the entire subduction zone. It reshapes where and how that danger might strike. A crack running straight through the descending slab creates a boundary, a seam in otherwise continuous rock. And seams do strange things when massive amounts of stress come rushing toward them during a major earthquake. Picture a sheet of paper you're trying to tear evenly in half. Sometimes the tear runs cleanly from one edge straight through to the other. Other times, the tear hits a weak spot, a fold, a crease, and it suddenly changes direction, jumping somewhere you didn't expect. Scientists worry a major earthquake rupture, racing along this fault system during a future megaquake, could behave the exact same way when it reaches one of these hidden cracks. Two very different outcomes are possible, and researchers openly admit they do not yet know which one is more likely. The crack could act like a natural stopping point, absorbing energy and preventing a rupture from spreading any further along the coast. Or it could act like a launching point, letting stress jump across the gap and trigger an even larger earthquake than anyone previously modelled for this stretch of coastline. Neither possibility has ever been tested against a real, modern megaquake, simply because this stretch of coast has not produced one in the age of seismic instruments. Scientists are left studying imaging, old earthquake records, and computer models, trying to guess how a piece of the Earth behaves during an event nobody alive has ever measured directly. That uncertainty sits at the centre of everything researchers are racing to understand about the crack itself, starting with its most puzzling feature. Some sections of it rumble constantly with small earthquakes. Other sections sit in complete, unsettling silence. Stretch a single, continuous fracture across nearly 47 miles of ocean floor, and you would expect it to behave the same way from one end to the other. It does not. Researchers studying this crack found something far stranger. Some stretches rumble constantly with small earthquakes. Neighbouring stretches, sometimes just a few miles away, sit in complete silence, producing no detectable earthquakes at all. At first glance, that pattern might look random, almost like static on an old radio. Scientists do not think it is random. They believe the pattern is telling them something specific about which parts of this massive crack have already torn completely apart, and which parts are still hanging on. Earthquakes happen when two surfaces of rock are still pressed together, still grinding, still catching against each other as they try to slide. That grinding produces friction, and friction produces the small shocks and tremors seismometers pick up constantly along active fault lines. Where researchers detected ongoing earthquake activity along this crack, they found evidence that the rock on either side is still connected, still locked, still fighting against itself. Where the earthquake stopped completely, something different appears to have happened. No grinding rock means no friction. No friction means no earthquakes. Silence, in this case, is not the absence of activity. It is evidence that two pieces of rock have already fully separated, drifting apart from each other with nothing left touching, nothing left to shake. Think about a rope being pulled apart, strand by strand. While threads are still connected, tugging on the rope produces vibration, resistance, sound. Once every single strand finally snaps, the two halves fall completely silent, no longer fighting against each other in any way. The silence marks the moment the separation finished, not the moment nothing was happening. Applied to the seafloor off Vancouver Island, that means the quiet stretches along this crack likely mark places where a piece of the Juan de Fuca plate has already broken away entirely, becoming its own independent fragment drifting slowly through the earth. The louder, still active stretches mark places where separation has not finished yet, where rock is still locked together, still capable of producing sudden, sharp earthquakes as it grinds apart. This gave researchers something they had never really had before, a second, completely independent way to confirm what their sound wave images were showing. The earthquake records lined up with the imaging almost perfectly. Quiet zones on the seismic map matched quiet zones on the sound wave images. Active zones matched active zones. Two totally different types of scientific evidence, pointing toward exactly the same conclusion. That kind of agreement matters enormously in science. Coincidences happen. A single unusual pattern in one dataset might be a fluke, an error in the equipment, or simple bad luck. Patterns that show up clearly in two unrelated datasets, gathered using two completely different methods, years apart, are much harder to dismiss as coincidence. Researchers grew increasingly confident that what they were looking at was a real, ongoing process, playing out right now, deep beneath the waves. A process that, once scientists understood it fully, turned out to look far less like a sudden catastrophe and far more like something almost mechanical. Not one single dramatic break. Dozens of smaller ones arriving one at a time spread across millions of years. Here is where the story gets personal for the scientists studying it. The single largest fracture in this entire system, the one where a slab of ocean floor dropped 3 miles straight down, has not gone silent yet. It is still producing small earthquakes. It is still connected, still grinding, still fighting to hold together. Researchers describe it almost like watching a branch crack under too much weight, snapped nearly all the way through, hanging on by threads of wood fibre that have not quite given out yet. The branch has not fallen. It is close. Every gust of wind tests exactly how close. Brandon Shuck, one of the researchers who led the analysis, put it plainly. This particular fault is not fully torn off yet. It is close. Those words carry enormous weight for anyone living along this coastline, because they mean the largest, most dramatic break scientists have found is not a finished event sitting quietly in the geological past. It is an active, ongoing process happening right now, somewhere beneath the waves most people will never think twice about. That raises an obvious question. What happens when this particular fault finally does separate completely? Researchers cannot simply wait around and watch, since the process could take anywhere from a handful of years to several more centuries to finish. Instead, they monitor the fault the same way doctors monitor a patient with an irregular heartbeat, checking seismic instruments regularly for any sign the pattern of small earthquakes along this stretch is shifting, growing more frequent or suddenly falling silent in a way that might signal the final separation is underway. Nobody knows for certain, and researchers are careful to say so honestly rather than pretend otherwise. Full separation might happen quietly, the last few connected threads of rock simply giving way over the coming decades without producing anything dramatic on the surface. Or it might happen suddenly, releasing whatever stress remains locked inside that last connected section all at once, in the form of a distinct, felt earthquake. Either outcome fits within what scientists already understand about how these tears behave elsewhere along the fault. Some sections apparently broke gradually, fading into silence over long stretches of time. Others may have snapped more abruptly, producing a burst of earthquakes before finally falling quiet for good. Without a direct, real-time example to compare against, researchers can only make educated guesses about which pattern this particular fault will follow. This fault draws extra attention for another reason too. Its location, sitting near the crowded, chaotic junction where the Explorer Plate, the Juan de Fuca Plate, and the edge of the continent all meet in the same tangled corner of the Earth. A major shift in one plate at a junction like this rarely stays isolated. Stress transferred through one connection can nudge pressure onto a neighbouring fault, occasionally triggering activity in places seismologists were not even watching that closely. For now, researchers keep monitoring this stretch of coastline the way you might watch a kettle, just before it boils, calm but paying close attention, aware that the moment of change could arrive without much warning at all. Zoom out far enough, though, and this single fault stops looking like an isolated event at all. It starts looking like one piece of a much stranger pattern, a pattern that stretches across the entire northern half of this subduction zone and across a timescale far longer than any human life could ever measure. Scientists have a name for the pattern stretching across that entire timescale. They call it piecewise termination, a term describing a structure that fails through many small separate breaks, rather than one single, sudden collapse. That name sounds complicated. The idea behind it is not. Imagine a long freight train derailing car by car over a long stretch of track, each one snapping loose from the one ahead of it at a different moment, rather than all crashing at once in a single dramatic wreck. From far away, watching the whole thing unfold, it would look chaotic, unpredictable, almost random. Zoom in close enough on any single car, though, and each individual break makes perfect sense on its own. That is roughly what researchers believe is happening to the Juan de Fuca Plate at its northern edge. Instead of the entire slab breaking away from the subduction zone in one massive catastrophic event, it appears to be coming apart section by section, each piece separating on its own timeline, sometimes millions of years apart from the piece next to it. Older models of subduction never accounted for this kind of staggered, uneven breakup, largely because nobody had ever caught one happening clearly enough to study. Brandon Shuck, the researcher who led the study, described it using almost the exact same image. Rather than one giant collision, scientists studying this fault are watching a slow-motion derailment, one section of track failing, then another, spread across a length of time no human mind can fully picture. Here is why that pattern matters beyond simple curiosity. Every time one piece of the plate fully detaches, the rest of the connected slab loses a small amount of the pull dragging it downward into the earth. Picture a chain of train cars rolling downhill, connected by couplers. Cut one car loose from the back, and the remaining cars keep rolling, slightly lighter, slightly less connected to whatever was pulling from behind. Cut enough cars loose, one at a time, and eventually the whole train slows down, then stops completely. Subduction zones work the same way, according to this new evidence. The weight of the sinking slab is part of what keeps the entire system moving, pulling more crust down behind it the way a falling chain pulls the rest of the chain over the edge of a table. Every piece that tears away and drifts off on its own reduces that pull slightly. Repeat that process enough times, across enough millions of years, and an entire subduction zone can eventually grind to a halt for good. Nobody suggests that outcome is close. Each individual episode of tearing plays out across millions of years, far slower than anything relevant to a human lifetime, a human century, or even a human civilization. But understanding this pattern gives scientists something they never had clearly before, a working model for exactly how a subduction zone dies, piece by piece, rather than all at once, built from direct evidence instead of guesswork. Every piece that breaks free during this slow collapse becomes something new, a fragment with its own name, its own path, and its own strange story to tell. Understanding exactly what one of those fragments looks like and what happens to it after it finally lets go turns out to matter more than anyone aboard that research ship first realized. Every piece that breaks free during this slow-motion collapse needs a name, and geologists already have one. They call each fragment a microplate, a small independent piece of crust no longer connected to the larger plate it once belonged to. Microplates are not rare or exotic on their own. Geologists have identified dozens of them scattered across the ocean floor worldwide, tiny scraps of crust left behind after larger plates broke apart, collided, or simply wore down over millions of years. Most are small enough that you could fit several of them inside a single Canadian province. Compared to giants like the Pacific Plate, which spans a large portion of the entire planet, a typical microplate looks almost like a dropped puzzle piece next to a finished picture. Once a fragment fully separates and becomes its own microplate, it stops behaving like part of its old, larger family. It develops its own direction of movement, sometimes drifting at a different speed, sometimes tilting or rotating slightly compared to the plate it broke away from. Imagine a chunk of ice carving off the edge of a much larger glacier. For years, that ice moved as part of one enormous connected sheet. The moment it breaks free, it becomes its own small iceberg, floating on its own path, no longer tied to the glacier's rhythm. Off the coast of Vancouver Island, researchers believe several sections of the Juan de Fuca Plate have already reached this stage, broken away completely, drifting independently beneath the ocean floor as their own small, largely forgotten fragments. These pieces are far too small and far too deep to notice from the surface. No mountain rises to mark their edges. No visible line on a map shows where one begins and another ends. Their existence is written entirely in sound wave images and decades of earthquake data. Evidence understood only by researchers willing to dig deep enough to find it. Studying a microplate might sound like a small technical detail buried inside a much bigger story. In reality, these fragments carry enormous scientific value because they represent something close to a fossil record of a process that normally takes far too long for anyone to observe directly. Geologists have found similar drifting fragments near other subduction zones around the Pacific Ocean, from the coast of Japan to the waters off New Zealand, each one offering a slightly different snapshot of the same slow, ongoing process happening at different speeds and different stages around the globe. A subduction zone dying takes millions of years. A single human lifetime cannot watch it happen from beginning to end. But scattered microplates, frozen in whatever position they held the moment they broke free, let scientists reconstruct that entire process after the fact, one fragment at a time, like piecing together a story from scattered chapters found out of order. That is exactly what happened next in this particular piece of research. Once scientists finally understood clearly what a freshly formed microplate looked like, hiding just off the coast of Vancouver Island, they realized they had already seen this same pattern somewhere else before. The scene sat thousands of miles away, off a completely different coastline, in rock that had gone cold and quiet millions of years before anyone thought to study it carefully. Off the coast of Baja California, far from Vancouver Island, scattered pieces of an ancient broken plate have puzzled geologists for decades. They belong to something called the Farallon Plate, once one of the largest slabs of ocean floor on the entire planet, stretching along most of the western edge of North America. The Farallon Plate no longer exists in any complete form. Over tens of millions of years, it slid beneath the continent piece by piece, melting into the mantle, feeding volcanoes, and eventually disappearing almost entirely from the surface of the Earth. Scattered fragments of it survived, abandoned pieces left behind in the rock record, scattered like shrapnel from an explosion that happened so slowly nobody alive witnessed it directly. That timescale is almost impossible to picture. The Farallon Plate began its slow disappearance, while dinosaurs still walked across what is now North America, and pieces of it were still sinking long after those dinosaurs vanished entirely. An entire slab of ocean floor can outlast an entire era of life on Earth, quietly dissolving into the planet's interior long after everything living on the surface above it has already come and gone. For years, those fragments confused researchers. Geologists could see the leftover pieces clearly enough in the rock, mapped and measured using the same imaging techniques applied everywhere else along the coast. What they struggled to explain was the process that produced them. Why would a single, massive plate break into scattered chunks instead of sliding beneath the continent as one smooth, continuous sheet, the way textbooks generally described subduction working? The answer sat undiscovered until researchers found a subduction zone caught in the exact same process, happening right now in real time, off the coast of Vancouver Island, rather than something already finished millions of years ago. Suzanne Carbot, one of the lead scientists behind the discovery, said her team had never had such a clear, direct picture of this kind of collapse actually happening before. Every previous example scientists had studied was already finished, already frozen into old rock, already impossible to observe directly in motion. Cascadia changed that. For the first time, researchers had a living example, an active subduction zone visibly tearing itself apart into microplates, in exactly the pattern that would eventually leave behind scattered fragments like the ones found off Baja, California. The mystery surrounding the Farallon Plate suddenly had a clear, modern explanation. It likely died the same way Cascadia's northern edge appears to be dying today, piece by piece, over an almost unimaginable stretch of time. This connection matters far beyond satisfying scientific curiosity. It means researchers are no longer just studying a strange local anomaly off the coast of British Columbia. They are watching a fundamental process that has shaped the entire western edge of North America for tens of millions of years, a process responsible for building mountains, fueling volcanoes, and quietly deciding which pieces of ocean floor survive and which ones vanish into the mantle forever. It also raises an unsettling question nobody can fully answer yet. If Cascadia truly is following the same path the Farallon Plate once followed, what does that mean for the region's most dangerous, most feared earthquake hazard? Does a subduction zone in the process of dying become safer over time, quieter, less capable of producing a massive quake? Or does the stress redistributing across these torn, fractured pieces somehow make the danger even harder to predict? Researchers are sharply divided on the answer, and their disagreement leads straight into one of the biggest open questions in earthquake science today. Ask two different earthquake scientists what this newly discovered crack means for future earthquake danger, and you might get two very different answers. Both would be backed by real evidence drawn from decades of careful fieldwork. Both would be entirely reasonable, argued by researchers who respect each other's work. Neither one can currently prove the other wrong. The first theory treats the crack as a kind of natural circuit breaker. During a future megaquake, when stress comes rushing along the subduction zone looking for somewhere to release, a deep fracture cutting through the plate could act like a barrier, absorbing energy and physically stopping the rupture from spreading any further north. Under this theory, the crack might actually reduce danger in some areas, containing a future earthquake to a smaller stretch of coastline instead of letting it run the entire length of the fault. The second theory paints a very different picture. Instead of blocking a rupture, the crack could act as a weak point that stress jumps across, almost like a spark leaping over a small gap between two wires. Under this theory, a major earthquake starting south of the crack could potentially reach it, jump across, and trigger additional rupture on the other side, producing a larger, more complex earthquake than models currently predict for this section of coastline. Both theories rely on real physics, and both have supporting examples from other fault systems studied around the world. Some documented ruptures have stopped cleanly at similar structural boundaries, sparing entire regions from damage that computer models had predicted was likely. Others have jumped across gaps scientists assumed would block them, surprising researchers with earthquakes larger and more far-reaching than anyone expected beforehand, sometimes rupturing along sections of a fault that had been considered separate, unconnected hazards for decades. The honest answer, the one researchers actually give when asked directly, is that nobody knows yet which outcome applies here. This crack has never produced a full-scale megaquake since scientists began recording earthquakes with modern instruments. There is no direct historical example to study, no past event to measure against, only models, comparisons to other fault systems, and careful analysis of the rock itself. That uncertainty is not a failure of the research. It is an honest reflection of how difficult this particular question really is. Earthquake science routinely deals with events too rare, too destructive, and too poorly recorded to study the way researchers might study something like weather patterns or ocean currents, phenomena that repeat often enough for scientists to build reliable models from direct observation alone. Sometimes the most responsible answer a scientist can give is simply that more evidence is needed before anyone can be certain, even when that answer feels unsatisfying to anyone hoping for a clear, confident prediction. What this discovery does provide, regardless of which theory eventually proves correct, is a far more detailed map than researchers had before. Every future model estimating how a Cascadia megaquake might unfold now has to account for this newly discovered fracture, built directly into the calculations rather than ignored as an unknown variable. Whichever theory eventually wins that scientific argument, one thing about this discovery deserves to be said clearly, without any confusion. It has nothing to do with making the region's oldest, most feared earthquake threat any smaller. Here is a detail worth stating as clearly as possible, because it is easy to misunderstand. Discovering that a subduction zone is tearing apart piece by piece does not mean the region has become safer. It does not shrink the danger scientists have warned about for decades. If anything, it adds detail to a threat that was already considered one of the most serious earthquake hazards in North America, long before anyone found this crack at all. Researchers involved in the discovery said this directly. The new images do not change how large an earthquake this stretch of coastline could produce on a timescale that matters to anyone alive today. Cascadia remains fully capable of generating a massive historic earthquake, the same conclusion scientists reached decades ago, based on entirely separate evidence gathered long before this expedition ever set sail. That separate evidence is worth understanding on its own, because it does not depend on cracks, microplates, or any of the discoveries covered so far. It comes from something far older, and in some ways far more convincing, evidence collected patiently over decades by geologists working with shovels, boats, and old paper archives long before anyone imagined towing sound wave equipment across this coastline. Buried sediment along the coastline, drowned forests still standing in salt water, written records from the other side of the entire Pacific Ocean, describing a wave that arrived with no earthquake ever felt beforehand. All of that older evidence points toward the same conclusion independently. This coastline has produced a massive history-altering earthquake before. Multiple times, in fact, based on layers of evidence stretching back thousands of years, long before scientists ever towed a research ship along this coast, or imaged a single fracture beneath the waves. The crack discovered off Vancouver Island adds a new layer of complexity on top of that older, already well-established danger. Imagine learning your house sits on a foundation with a known structural weakness, something engineers have tracked and worried about for years. Then imagine an inspector finds an additional crack somewhere else in the foundation, a separate issue entirely. Finding that second crack does not fix the first problem. It simply means there is more for engineers to study, more variables to account for, more reasons to take the whole structure seriously. That is roughly the position scientists find themselves in today along the Cascadia coastline. One well-documented, centuries-old danger, proven through multiple independent types of evidence. One brand new, still poorly understood complication, discovered only recently, that could theoretically make certain earthquake scenarios worse, or in a more hopeful outcome, slightly more contained. Both pieces of evidence point toward the same coastline, the same stretch of ocean floor, and ultimately the same question every scientist working on this research keeps circling back toward. Whether Cascadia is dangerous was settled decades ago, through evidence strong enough to convince even skeptical researchers. The open question now is when the coastline's largest, most feared earthquake will finally strike again, and just how much worse a newly discovered actively tearing fault might make it. To understand that older, more established danger fully, you have to travel back more than 300 years to a single night in January when an entire coastline dropped without warning and a tsunami crossed the widest ocean on Earth before anyone even knew an earthquake had happened at all. Every scientist working along this coast, from the ocean floor mappers off Vancouver Island to researchers tracking small earthquakes near the Nootka Fault, is quietly circling the same question. When will Cascadia produce the earthquake this entire subduction zone was built to produce? A full-margin megaquake far larger than almost anything ever recorded on this continent. Scientists have a name for it, spoken almost like a title. The Big One. It is not a nickname invented for headlines or documentaries. Researchers, engineers, and emergency planners use the term seriously in official reports and government planning documents, because no other phrase captures the true scale of the disaster this fault could eventually unleash. Here is the number that anchors every conversation about it. Magnitude 9. Every full step upward on the earthquake scale multiplies the shaking by roughly 10 times, and the energy released by roughly 30 times. A magnitude 9 earthquake sits 3 full steps above the magnitude 6 range, the range strong enough to seriously damage poorly built structures. Multiply the destructive power across 3 of those steps, and the result is almost impossible to compare to anything in daily life. The closest comparison most people have actually witnessed happened across the Pacific Ocean, in northeastern Japan, in 2011. That earthquake also measured about magnitude 9. It killed close to 16,000 people, destroyed entire towns, and triggered a nuclear disaster that reshaped an entire country's energy policy for a generation. Cascadia is capable of producing an earthquake in that exact same class, rupturing along the same kind of megathrust boundary, in almost the same geological setting. Engineers and emergency planners across the Pacific Northwest studied the Japan disaster closely, treating it almost like a preview of what their own coastline could eventually experience. Footage from that event, walls of water sweeping across farmland and through entire neighborhoods, gave planners on this side of the ocean a level of detail no computer model could fully capture, and it accelerated building code changes across the region within just a few years. The difference between Japan in 2011 and the Pacific Northwest today comes down to timing and memory. Japan has a long, well-documented history of large earthquakes, passed down through written records stretching back centuries, reinforced by regular smaller quakes that keep the danger fresh in public memory. Cascadia has gone quiet for so long that most people living directly on top of it have never felt anything close to a serious warning sign. That silence is not evidence of safety. It is closer to the quiet stretch of a fuse burning down out of sight. Scientists know the fault is there. They know its rough size. They know it has ruptured catastrophically before more than once based on physical evidence buried in the coastline itself and the seafloor offshore. What nobody can tell you, with any real precision, is exactly when it will happen again. The last time this fault let go completely, it did so on a single night, without warning, after the sun went down. The shaking that followed dropped an entire stretch of coastline by several feet in a matter of minutes, drowned coastal forests in salt water, and launched a wave that crossed the widest ocean on Earth. Piecing together exactly what happened that night, and exactly when it happened, became one of the strangest detective stories in the history of Earth science, solved using old paper records on the opposite side of the planet, and trees still standing exactly where they died, rather than any modern instrument. Picture the coastline of what is now Washington, Oregon, and southern British Columbia, sometime after dark in the winter of 1700. No highways ran along this stretch of coast. No cities stood where Seattle, Portland, or Victoria exist today. Indigenous communities lived along rivers, inlets, and beaches, following patterns of fishing, hunting, and travel developed over thousands of years. Then, without warning, the ground began to shake harder than anyone living had ever felt before. Based on physical evidence gathered since, scientists believe the rupture began deep beneath the ocean floor, somewhere along more than 600 miles of locked fault, stretching from northern California to Vancouver Island. Once the rupture started, it likely spread outward in both directions within a matter of minutes, releasing centuries of stored pressure all at once, the exact same kind of stored pressure researchers still track today, using GPS stations bolted to the coastline. The shaking itself probably lasted several minutes, far longer than anything most people alive today have ever experienced. Survivors would have felt the ground roll and lurch beneath them continuously, long enough for many to wonder whether it would ever stop. Fires likely broke out in some communities soon after the shaking finally settled, sparked by cooking fires and hearths knocked loose during the violent motion, a common and often overlooked danger following any major earthquake. Landslides almost certainly swept down steep coastal slopes as well, triggered by the same shaking, adding a second wave of destruction on top of whatever damage the earthquake itself had already caused. When it finally did stop, the coastline itself had changed. Evidence buried in coastal soil shows the ground near the shore dropped by several feet almost instantly, the same kind of sudden vertical motion capable of triggering a tsunami. Areas that had been dry land, home to forests and grazing animals, sank low enough for seawater to rush in and stay, permanently drowning entire groves of trees within minutes. Communities living along this coast would have had almost no time to process what had just happened, before an entirely new danger arrived. Survivors of the shaking, still finding their footing on ground that had just dropped beneath them, would soon have needed to flee again, this time from walls of water racing in from the sea, arriving within minutes of the shaking finally stopping. Oral traditions passed down through generations of indigenous communities along this coast describe events matching this kind of catastrophe. Stories of the ground shaking violently, of villages destroyed, and of waves rushing inland without warning. These accounts, carried forward for centuries before anyone wrote them down, describe details that align remarkably closely with the physical evidence scientists have since uncovered independently. Evidence buried in soil, sediment, and tree rings up and down the coast. Nobody living in the region at the time had a written language capable of recording an exact date, at least not in the way modern researchers would recognize one. For nearly 3 centuries, that meant the story of this earthquake could be reconstructed only in general terms, sometime in the late 1600s or early 1700s, based on rough estimates from tree rings and layers of disturbed soil. Then, in the 1990s, researchers found something nobody expected. Written proof of the exact night this earthquake struck, sitting quietly in centuries-old paper records on the opposite side of the Pacific Ocean, in a country that never felt so much as a single tremor from the event. On the coast of Japan, in the early hours of January 27, 1700 local time, something strange happened. Waves suddenly rushed in from the ocean, flooding rice fields, damaging homes, and destroying at least one saltworks operation along the shore. Local officials recorded the event carefully, the way coastal communities often tracked unusual flooding, noting the date, the damage, and the details of what people witnessed. Here is what made this particular flood strange enough to remember for centuries. Nobody in Japan felt an earthquake beforehand, no tremor, no rumble, nothing to warn residents that a wave might be coming. Waves simply arrived out of a calm sea, seemingly from nowhere. Local samurai officials in several coastal villages recorded the flooding in careful administrative detail, the kind of routine bureaucratic paperwork nobody at the time expected future scientists on the other side of the planet to ever read again. Those records described flooded rice paddies, damaged homes, and salt production facilities ruined by the sudden intrusion of seawater, ordinary disaster reporting that happened to preserve something extraordinary without anyone realizing it at the time. Japanese coastal communities knew tsunamis extremely well, long before modern science explained how they worked. Nearly every tsunami they had ever experienced followed a local earthquake, shaking strong enough to send people running before the water ever arrived. A tsunami with no earthquake attached to it made no sense within that understanding. Researchers centuries later gave this kind of event a fitting name, an orphan tsunami, a wave that arrived without any local parent earthquake to explain where it came from. For nearly 300 years, that mystery sat unsolved. Then, in the 1990s, a team of geologists studying the Pacific Northwest coastline connected 2 completely separate lines of evidence that nobody had previously thought to combine. American researchers had already gathered physical proof of a massive earthquake striking the Cascadia coastline sometime around 1700, Based on drowned forests and disturbed soil layers, Japanese researchers, working independently, had preserved centuries-old written records describing an unexplained tsunami striking their coast on a specific night in January of that same year. Once both groups compared notes, the picture snapped into focus immediately. A massive earthquake off the coast of North America could send a tsunami racing across the entire width of the Pacific Ocean, arriving in Japan roughly 10 hours later, long after any shaking on the American side had already stopped. Japan felt the wave. North America felt the earthquake. Nobody at the time had any way of connecting the two events across an ocean that wide. Using the exact timing recorded in Japanese records, researchers worked backward and pinpointed almost the precise moment the Cascadia earthquake struck on the other side of the ocean, a level of precision nobody expected to achieve for an earthquake, with no written record anywhere near where it actually happened. A tsunami with no local earthquake solved a 300-year-old Japanese mystery. A tsunami with no witness on the American side confirmed exactly how violent this coastline's history really is. Few scientific stories illustrate international collaboration quite this vividly. Researchers working an ocean apart, studying completely different types of evidence, in completely different languages, ended up filling in each other's biggest missing piece almost by accident, decades after both puzzles had first been noticed. That same violent history left behind a second kind of proof much closer to home, standing quietly along the coast for anyone willing to look. Entire forests killed instantly, still standing exactly where they died. Along stretches of the Washington and Oregon coastline, and in scattered pockets near the southern tip of Vancouver Island, dead trees still stand upright in salt marshes, bleached grey, roots submerged in water that should never have reached them. Locals call these eerie groves ghost forests, and for years nobody fully understood why they existed. Trees do not simply die standing upright in saltwater by accident. Western red cedar and Sitka spruce, the dominant species in these dead groves, cannot survive prolonged exposure to salt. Something must have flooded these forests suddenly and permanently, killing entire stands of trees within a short window, then kept them submerged long enough that they never had a chance to recover. Early researchers who first noticed these ghostly groves considered several possible explanations before settling on the correct one. Some wondered whether rising sea levels alone might explain the flooding, a gradual process playing out over centuries. That explanation eventually fell apart once scientists examined how abruptly these trees had died, all at once rather than slowly declining over generations. Geologists eventually connected these ghost forests directly to the same earthquake responsible for the orphan tsunami in Japan. When the Cascadia coastline dropped several feet during the 1700 earthquake, low-lying forests standing safely above the tide line suddenly found themselves sitting at or below it. Seawater rushed in and stayed, drowning root systems never built to handle saltwater exposure. Here is where these dead trees became something far more valuable than a strange local landmark. Trees add a new growth ring every year, and the pattern of thick and thin rings within any single tree can often be matched against rings from other trees in the same region, creating a shared timeline researchers call a chronology. By comparing ring patterns from dead ghost forest trees against patterns from nearby living trees with known ages, scientists could work out almost exactly which year each ghost forest tree stopped growing entirely. The results lined up with stunning precision. Trees in ghost forests across multiple sites, separated by significant distances along the coast, all stopped growing during the exact same year, matching the same winter identified independently through the Japanese tsunami records. Two completely different types of evidence, one on paper on the other side of an ocean, one written inside the wood of trees that never moved an inch, arrived at the same conclusion from two entirely different directions. That kind of agreement, arrived at independently through such different methods, is about as close as earth science gets to certainty. Scientists no longer treat the 1700 Cascadia earthquake as an educated guess pieced together from scattered clues. They treat it as one of the most precisely dated earthquakes in the geologic record, more exactly timed in some ways than earthquakes that struck with modern seismometers already running. Some of these ghost forests remain standing today, more than 3 centuries after the earthquake that created them, visible to anyone willing to hike the right stretch of shoreline. Each dead trunk works almost like a frozen clock, its rings stopped on the exact same winter, a silent witness to the same violent night described independently through Japanese paperwork on the opposite side of the world. Ghost forests and orphan tsunamis both tell the story of a single earthquake. To understand how often earthquakes like this one actually strike this coastline, researchers had to look somewhere far stranger than tree rings or old paper records. They had to go looking in the mud, buried deep beneath the open ocean, far from any coastline at all. Every time a massive earthquake shakes the Cascadia coastline, it does something far offshore that has nothing to do with tsunamis, drowned forests, or shaking felt on land. It triggers underwater landslides, sending huge volumes of mud and sand cascading down submarine canyons and settling across the deep ocean floor in a distinct, recognizable layer. Geologists call these underwater landslide deposits turbidites, and researchers studying the seafloor off the Pacific Northwest coast realize something remarkable. Every layer represents a moment in time, a snapshot of a single earthquake violent enough to shake loose that much sediment all at once. Stack enough of these layers on top of each other, drilled up from the ocean floor in long cylindrical cores, and you get something close to a diary written entirely in mud, one entry for every major earthquake this coastline has produced. Collecting these cores requires research ships lowering long hollow tubes straight down into the seafloor, sometimes through more than a mile of open ocean, then pulling up a cylinder of undisturbed mud stacked in the exact order it originally settled. Reading one of these cores from top to bottom is a little like reading a book from the most recent page backward, each layer older than the one sitting directly above it. Researchers have pulled cores containing these layers from dozens of sites, scattered along the entire length of the Cascadia margin, then carefully dated each layer using the same radiocarbon techniques archaeologists use to date ancient artifacts. The results stretch back roughly 10,000 years, an extraordinary window into the region's earthquake history, far longer than any written record could ever provide. Inside that 10,000-year diary, researchers found evidence of at least 41 major earthquakes. Some of those events ruptured the entire length of the fault at once, producing a full-scale big one roughly 19 separate times throughout that record. Others ruptured only the southern portion of the fault, producing smaller, though still serious earthquakes far more frequently than the full margin events. Here is where the story gets genuinely strange. Earthquakes along this fault do not arrive on a neat, predictable schedule. The mud record shows clusters, several major earthquakes striking within a few centuries of each other, followed by unusually long, quiet stretches lasting many centuries before the pattern repeats. Full margin earthquakes, the true big one events, have struck anywhere from a couple hundred years apart to well over 500 years apart, based on this same buried record. That irregularity makes forecasting extremely difficult. A fault that ruptured like clockwork every exact number of years would be far easier to predict than one following this kind of clustered, uneven pattern. Scientists studying the mud record openly admit that spacing between past earthquakes offers hints, but never a guarantee about when the next one will strike. Some clusters in the record pack 4 or 5 major earthquakes into a span of a few hundred years, followed by gaps stretching close to 1,000 years before the pattern begins again. A rhythm nobody has yet fully explained. What the sediment diary does provide, with far more confidence than guesswork ever could, is something almost as valuable. A rough set of odds, built from real data instead of speculation, describing roughly how likely this coastline is to produce another massive earthquake within any given stretch of time, including the exact stretch of time everyone alive today happens to be living through. Ask a Cascadia researcher for a single number describing the danger, and most will give you something close to this. Somewhere around a 1 in 7 chance that a full margin megaquake strikes this coastline within the next 50 years. That number comes directly from the mud record buried in cores pulled from the ocean floor, combined with additional evidence gathered on land. Researchers plug the timing of past earthquakes into statistical models, originally developed to study patterns of rare, clustered events. The same kinds of models used in other fields to estimate the odds of things like major floods or rare disease outbreaks. Applied to 19 full margin earthquakes spread across roughly 10,000 years, With the clustering and gaps included, those models produce a rough probability rather than a precise prediction. 1 in 7 might sound low enough to dismiss. Stretch the same math out to the year 2100 instead of 50 years from now, and the odds climb closer to 1 in 3. Compare either number to something more familiar. The odds of a home in a hurricane-prone region of the United States sustaining serious storm damage during a typical 30-year mortgage sit in a broadly similar range, a risk most homeowners in those regions take seriously enough to buy specific insurance and reinforce their houses against it. Insurance companies operating across the Pacific Northwest already factor numbers like these directly into how they price coverage, treating the Cascadia hazard with the same seriousness actuaries apply to hurricanes, floods, or wildfires elsewhere on the continent. That quiet financial acknowledgement, playing out in policy documents most homeowners never read closely, reflects just how seriously the professionals responsible for managing risk already take this particular number. The odds change further depending on where along the coast you happen to be standing. Researchers studying the mud record found that the southern portion of the fault, roughly the coastline of southern Oregon and northern California, ruptures far more frequently than the northern portion closer to Vancouver Island. Smaller, more frequent earthquakes near the southern end pull the overall odds upward for that specific stretch of coastline, while the northern end, including the waters off Vancouver Island where this entire story began, tends to wait longer between major full-margin events. That regional difference matters enormously for anyone trying to plan around this risk. A 1 in 7 chance is not a certainty, and it is not something to panic over immediately. It is also not a number small enough to ignore, especially for infrastructure built to last decades, bridges, hospitals, schools, and pipelines that could easily still be standing whenever this fault finally does let go again. Governments across the region have already started treating this number seriously, building new codes, retrofitting older buildings, and running large-scale earthquake drills based on exactly this kind of probability. None of that preparation can tell anyone the exact day the fault will finally rupture. What it can do is shape how much damage that rupture eventually causes, and that distinction, preparation instead of prediction, may be the single most important idea in this entire story. Understanding those odds is one thing. Understanding what a magnitude 9 earthquake would actually do to the city sitting directly on top of this fault today is something else entirely, and considerably harder to imagine. Picture the ground shaking continuously for 4 to 6 minutes, far beyond the few seconds most people associate with an earthquake, and well past even the roughly 2 minutes recorded during the 2012 Haida Gwaii earthquake, Canada's second largest quake on record. 4 to 6 full minutes, long enough to walk from one end of a football field to the other and back again, all while the ground beneath your feet refuses to hold still. That length of shaking is what researchers expect from a full-margin Cascadia megaquake, based on comparisons with similar earthquakes recorded elsewhere around the Pacific Ocean. Duration matters enormously for how much damage a quake causes, because buildings, bridges, and pipelines that might survive a short, sharp jolt can fail under prolonged, repeated stress, the same way a paperclip eventually snaps after being bent back and forth enough times. Engineers use exactly that kind of repeated bending when testing how structures respond to earthquakes, shaking scale models on specialized platforms for minutes at a time rather than seconds, specifically to study how fatigue builds inside materials that might otherwise appear to hold steady through a shorter burst of shaking. Along the coastline itself, shaking this strong would trigger landslides on steep, saturated slopes, collapse older buildings never designed with modern earthquake codes, and severely damage bridges, highways, and rail lines connecting coastal communities to the rest of the region. Cities including Victoria, Vancouver, Seattle, and Portland would all feel strong, damaging shaking, even though every one of them sits a meaningful distance from the fault itself. Emergency planners in this region have run detailed scenarios modelling exactly this kind of earthquake, and the results consistently point toward the same conclusion. Damage would not be limited to a single city or a single type of structure. Older, unreinforced brick buildings would be especially vulnerable, along with older bridges and elevated highways built before engineers fully understood how this fault behaves. water mains, sewer lines, and underground power cables could suffer widespread breaks across a huge area all at once, rather than in a single, easily repaired location. The scale of that damage would strain emergency response in ways smaller earthquakes never do. Roads needed to bring in supplies, and rescue teams could themselves be blocked or destroyed. Hospitals could be damaged at the exact moment they are needed most. Communication networks could fail across the region simultaneously, making it difficult for emergency services to even understand the full scope of what happened in the first several hours. None of this is meant to describe an inevitable, unavoidable disaster. Building codes across the region have improved significantly since scientists first understood the true scale of this hazard, and newer buildings, bridges, and hospitals are increasingly designed specifically to survive an earthquake this large. The gap between older infrastructure and newer, earthquake-resistant construction may end up being the single biggest factor determining how the region actually experiences this event whenever it finally arrives. Retrofitting older schools and hospitals has become a specific funded priority across several coastal cities. A slow, expensive process that nonetheless chips away at the gap year by year. Shaking this severe is only part of the danger. The same earthquake responsible for all of this damage on land would also trigger something happening entirely underwater, racing toward the coast at the speed of a passenger jet, and arriving in some places before the shaking on land has even finished. A magnitude 9 earthquake along the Cascadia megathrust would not just shake the coastline. It would shove an enormous section of ocean floor upward or downward in an instant, displacing a wall of seawater above it, and sending that water racing outward in every direction as a tsunami. For communities sitting directly on the open Pacific coastline, places like Tofino on the west side of Vancouver Island, or the outer beaches of Washington and Oregon, the danger arrives almost immediately. Modelling suggests the first waves could reach some exposed coastal communities in 15 to 20 minutes, barely enough time to reach higher ground on foot, let alone by car through streets already damaged by minutes of violent shaking. For places sitting this close to the fault, the shaking itself becomes the warning. Anyone who feels the ground move for that long, right along this stretch of coast, is expected to move to high ground immediately, without waiting for any official alert. Emergency planners describe this simple rule using 3 memorable words, repeated constantly in coastal safety campaigns across the region. Long, strong, get gone. If the shaking lasts a long time and feels strong enough to knock you off balance, the correct response is to move toward high ground immediately, on foot, without waiting to gather belongings or check a phone for confirmation. Here is a detail that surprises most people learning about this risk for the first time. Major cities like Vancouver and Victoria sit at least partially protected from the worst of an open ocean tsunami, shielded by the bulk of Vancouver Island itself, along with the narrow winding waterways separating the island from the mainland. A wave racing toward the open coast has to bend, slow down, and lose energy working its way through these protected inland waters, arriving later and considerably smaller than it would along an exposed beach facing the Pacific directly. That protection is real, but it is not complete. Modelling still shows meaningful wave activity reaching inland waterways, capable of flooding low-lying areas, damaging ports, marinas, and waterfront infrastructure, and creating dangerous currents around bridges and narrow channels, even without producing towering walls of water downtown. Communities along the open coast face by far the most severe direct danger, while cities further inland face a serious, though comparatively smaller, secondary threat. Port facilities handling shipping traffic for the entire region sit directly along these inland waterways, meaning even a smaller wave could disrupt supply chains extending far beyond the immediate coastline. Studying the 2011 Japan tsunami gave researchers an unusually detailed modern example of how a real Cascadia-scale event might actually unfold along a similarly shaped coastline. Waves in Japan reached heights of over 100 feet in some narrow inlets, funneled and amplified by the shape of the coastline itself, while nearby areas with different geography saw considerably less severe flooding. Cascadia's coastline includes plenty of similarly shaped inlets and river mouths, capable of funneling and amplifying a future wave in exactly the same unpredictable way. meaning two neighbouring towns could end up facing dramatically different levels of danger from the exact same earthquake. Every layer of this hazard, the shaking, the tsunami, and one additional danger still to come, becomes dramatically worse in certain types of terrain. Soft, waterlogged ground sitting directly beneath some of the region's most heavily populated neighbourhoods. Solid ground seems like the one thing you can always count on. Liquefaction is the reason that assumption sometimes fails completely during a major earthquake. Certain types of soil, particularly loose, waterlogged sand and silt, behave in an unusual way when shaken violently enough. Under normal conditions, grains of sand sit packed together, touching each other directly, solid enough to support the weight of buildings, roads and bridges above. Violent shaking can force water trapped between those sand grains to suddenly take on more of that weight instead, pushing the grains apart just enough that the ground stops behaving like a solid and starts behaving like a thick, unstable liquid. Picture wet sand at the edge of the ocean, the kind that ripples and jiggles slightly when you stomp on it near the waterline. Liquefaction is that same effect, scaled up dramatically and triggered by earthquake shaking instead of a footstep. Buildings sitting on ground that liquefies can sink unevenly, tilt sideways, or in severe cases, sink several feet into ground that used to feel completely solid. This danger matters enormously for one particular stretch of the Vancouver region, built almost entirely on exactly this kind of unstable soil. The Fraser River Delta, home to the city of Richmond and several neighbouring communities, sits on layers of sand and silt deposited by the river over thousands of years. Soil scientists have specifically studied and mapped for liquefaction risk. Researchers drilling test sites across Richmond found that the overwhelming majority of locations tested showed high or very high potential for liquefaction during a strong earthquake scenario. Richmond sits on deltic soil reaching depths of several hundred feet in places, layered sand and silt built up slowly by the Fraser River over thousands of years of flooding and sediment deposit. That same soft, waterlogged ground that makes the delta such fertile farmland also makes it exceptionally vulnerable to shaking that turns solid earth into something closer to quicksand. That risk extends directly to the infrastructure people depend on most during an emergency. Highways and bridges connecting Richmond to the rest of the region, cross-ground identified as highly vulnerable to liquefaction, meaning the exact roads needed to evacuate or bring in emergency supplies could themselves become impassable at the worst possible moment. Underground water and sewer lines running through this same soil face a similarly elevated risk of breaking apart. Scientists studying the region found physical proof this has already happened before, buried in the ground itself. Sites across the Fraser Delta contain sand dikes and other telltale liquefaction features dating back thousands of years, some tied specifically to earthquakes matching the size and timing of previous Cascadia megaquakes. The ground beneath Richmond has liquefied during major earthquakes before, and researchers see no reason to expect anything different during the next one. None of this means the region is defenseless. Engineers can strengthen soil beneath new construction, reinforce foundations, and design bridges specifically to survive ground that temporarily behaves like liquid. Much of that work is already underway across the Vancouver region, informed directly by the same liquefaction maps researchers built by testing the ground itself, site by site, one core sample at a time. Every hazard covered so far, the shaking, the tsunami, and the liquefied ground traces back to the same massive fault running the length of this coast. A smaller, stranger fault sits much closer to where this entire story began, and it carries its own separate, complicated history. Return to the fault responsible for the July earthquake that opened this entire story, and one more layer of its history comes into focus, a history stretching back millions of years before anyone imagined studying it with sound waves and research ships. The Nootka Fault formed roughly 4 million years ago, when a smaller volcanic ridge, the same kind of underwater mountain range that constantly builds new ocean floor, broke away from its larger neighbour and started spreading in a slightly different direction. That split created two separate systems where there had previously been one, and somewhere had to absorb the difference in motion between them. The Nootka Fault became that boundary, a long scar cutting between the newly independent Explorer Plate and its larger relative, the Juan de Fuca Plate. Unlike the main subduction boundary running the length of Cascadia, where one slab dives directly beneath another, the Nootka Fault works through an entirely different kind of motion. The two plates on either side slide horizontally past each other, similar to the sideways grinding responsible for the July earthquake described back at the very beginning of this story. Geologists measure that sideways motion at roughly an inch every year, a pace almost identical to the speed of the Juan de Fuca Plate diving beneath the coast, just aimed in a completely different direction. Picture two long conveyor belts running side by side, moving at nearly the same speed but pointed in slightly different directions. Wherever their edges touch, friction builds between them exactly the way it builds along any other fault, regardless of whether the motion involved is a plate sliding downward or simply sliding sideways past its neighbour. That sideways grinding makes the Nootka Fault one of the most seismically active spots anywhere off the coast of British Columbia. Small earthquakes strike here constantly, far more often than almost anywhere else nearby, most too weak for anyone to feel. Occasionally, the fault produces something considerably stronger. Historical records show earthquakes along this exact fault reaching magnitude 6 and above, strong enough to be felt clearly across much of Vancouver Island, though rarely strong enough to cause serious damage given how far the fault typically sits from major population centres. Researchers monitoring this region closely in recent years identified an entirely new branch of the fault system nobody had previously mapped in detail, discovered only after a magnitude 6.4 earthquake struck along it, followed by a lengthy sequence of smaller aftershocks. That kind of discovery, an active fault hiding in plain sight for decades before finally announcing itself with a strong earthquake, is far from unusual in this particular corner of the ocean. The tangled, crowded geometry created by three separate plates crashing into the same small area keeps producing surprises for researchers who thought they already understood this stretch of seafloor completely. The Nootka Fault does not produce earthquakes anywhere near the scale of a full Cascadia megaquake. What it does instead is keep this entire region under near-constant seismic surveillance, generating enough small, frequent earthquakes that researchers have unusually detailed, real-time data on exactly how this crowded corner of the planet behaves. That constant background activity occasionally clusters into something stranger still, weeks at a time when hundreds of earthquakes strike the same small stretch of ocean floor in rapid succession. Most earthquakes follow a familiar pattern. One larger main shock strikes first, followed by a series of smaller aftershocks that gradually fade out over the following days and weeks. Every earthquake covered so far in this story, including the magnitude 5.6 quake that opened it, roughly follows that same basic pattern. Every so often, this stretch of coastline breaks that pattern entirely, producing something scientists call an earthquake swarm instead. A swarm looks completely different from a normal sequence. Instead of one clear main shock followed by fading aftershocks, a swarm produces dozens, sometimes hundreds, of earthquakes clustered tightly together in time and location, often without any single dominant event standing out clearly above the rest. One of the more striking examples struck the waters off Vancouver Island in recent years, when researchers recorded several hundred separate earthquakes within a span of just a few weeks, concentrated in one relatively small patch of ocean floor. Most of these earthquakes registered as fairly minor, somewhere in the magnitude 3 to 5 range, but the sheer number arriving in such a short window caught the attention of seismologists monitoring the region closely. News of the swarm spread quickly among residents of northern Vancouver Island, many of whom felt at least one or two of the stronger tremors directly. Local officials fielded a steady stream of questions during those weeks, residents wanting to know whether the unusual cluster of activity meant something bigger was building. Questions seismologists could only answer honestly with careful, measured uncertainty rather than firm reassurance. A seismologist with Natural Resources Canada described the area at the time as an unusually active, complicated tectonic setting, a place where oceanic plates are actively being formed while simultaneously being pushed toward the continent, all while separate faults nearby allow those same plates to slide sideways past one another. That combination, plates spreading, sinking and sliding all within the same small stretch of ocean, makes this particular corner of the coast especially prone to producing swarms rather than more typical main shock sequences. Here is what makes swarms so difficult to interpret in the moment. A normal earthquake sequence gives scientists a clear signal, a big shock followed by a predictable decline in aftershock activity. A swarm gives no such clear signal. Nobody monitoring one in real time can say with confidence whether the sequence has already peaked, whether it will simply fade out on its own within days, or whether it might be building slowly towards something considerably larger. Scientists studying swarms elsewhere around the world have documented cases where activity faded away completely within weeks, and other cases where a swarm eventually preceded a genuinely large, damaging earthquake nearby. That uncertainty is exactly why researchers treat every swarm along this coast with heightened attention, rather than dismissing it as routine background noise. Sideways, strike-slip motion, the same kind responsible for most swarm activity in this region, rarely produces a tsunami on its own, which offers some reassurance. It offers no guarantee at all about what a cluster of earthquakes might be quietly building toward deeper underground, out of sight, in exactly the kind of crowded, tangled fault system this entire stretch of coastline has turned out to be. Monitoring swarms like this one requires instruments capable of detecting an earthquake within seconds of it happening. The exact same kind of technology now protecting millions of people living along this coast every single day. Every earthquake covered throughout this story arrived without warning, felt only once the shaking had already begun. As of recent years, that is no longer entirely true for people living across the most earthquake-prone regions of Canada. In the spring of 2024, Natural Resources Canada activated a National Earthquake Early Warning System across British Columbia, connecting hundreds of sensors scattered throughout the province's highest risk zones. That system exploits a strange but useful quirk of physics. Earthquakes send out two different kinds of shock waves simultaneously. The first kind, called a P wave, travels fastest but rarely causes serious damage on its own. The second kind, the S wave, travels somewhat slower, but carries the powerful, damaging shaking most people associate with a serious earthquake. Sensors scattered across the region detect that faster, gentler P wave the instant an earthquake begins, instantly relaying the information to computers that calculate the earthquake's size and location within seconds. Armed with that information, the system can estimate almost immediately how strong the shaking will eventually become in any given area, and how much time remains before the slower, more damaging wave actually arrives. For places sitting a meaningful distance from the earthquake itself, that gap between the two waves can translate into several genuinely useful seconds, sometimes stretching into tens of seconds, of advance warning before the strongest shaking begins. Alerts reach the public automatically through cell phones, television, and radio, giving people just enough time to drop to the ground, take cover under something sturdy, and hold on before the real shaking starts. Similar systems already operate in Japan and Mexico, two other countries sitting along the same ring of fire responsible for so much of the earthquake activity covered throughout this story. Canada's system draws directly on lessons learned from those earlier programs, adapted specifically to fit the geography, population centres, and unique fault systems found along this particular stretch of coastline. Individual seconds might sound like an unimpressive amount of warning. Applied across an entire region simultaneously, those seconds add up to something far more significant than personal safety alone. Critical infrastructure operators receive these same alerts automatically, often faster than any human could react manually, triggering protective measures without waiting for a person to make a decision. Trains can automatically slow down or stop before derailing. Bridges and tunnels can halt incoming traffic before more vehicles enter a structure that might be damaged. Even fire station doors can be programmed to open automatically the instant an alert arrives, preventing shaking from jamming them shut at the exact moment emergency crews need to respond. This system cannot predict earthquakes before they happen, and it offers no warning at all to anyone standing extremely close to where the rupture actually begins, since the shaking there arrives before any alert has time to travel. What it can do is buy precious seconds for everyone else across a wide region, converting a portion of an earthquake's warning time from zero into something measurable, seconds that genuinely matter. When a false step, a falling shelf, or an unsecured bookcase can mean the difference between walking away and serious injury, Systems exactly like this one exist because of decades spent studying earthquakes, just like the one that opened this entire story. Patient scientific work that rarely makes headlines until the technology it produces finally saves someone's life during the earthquake nobody saw coming. Every earthquake examined so far in this story either struck relatively small, like the magnitude 5.6 quake off Vancouver Island, or struck so long ago that nobody alive today felt it firsthand, like the magnitude 9 megaquake of 1700. One earthquake sits squarely between those two extremes, close enough in time that plenty of people remember it clearly, and large enough to rank among the most powerful earthquakes ever recorded on Canadian soil. On the night of October 27, 2012, a magnitude 7.8 earthquake struck off the coast of Haida Gwaii, a remote island chain sitting off the northern coast of British Columbia. It remains the second largest earthquake ever instrumentally recorded in Canadian history, surpassed only by an even larger magnitude 8.1 quake that struck the same general region back in 1949. The shaking itself lasted somewhere between 1 and 2 full minutes on Haida Gwaii, an extraordinarily long stretch of ground motion by ordinary standards, though still considerably shorter than the 4 to 6 minutes scientists expect from a true Cascadia megaquake. The quake was felt across an enormous area, registering as far away as the Yukon, Alberta, and even parts of Montana, roughly 1,000 miles from where the earthquake actually struck. The earthquake also triggered a small tsunami, with waves reaching several feet in height at some points along the nearby coastline, though nothing close to the towering walls of water a full Cascadia megaquake could eventually produce. Residents of Haida Gwaii, familiar with the region's earthquake history, evacuated to higher ground quickly and calmly, a response emergency planners later pointed to as a model for how coastal communities elsewhere might react during a far larger future event. Remarkably, an earthquake this powerful caused very limited damage and no direct deaths. Several factors combined to produce that fortunate outcome. Haida Gwaii is sparsely populated, and the earthquake's rupture occurred more than 37 miles from the nearest population centres, giving the worst of the shaking room to weaken before reaching anyone's home. Local building styles also helped considerably. Most structures on the islands are low, wood-frame buildings, a style of construction that generally flexes and absorbs earthquake shaking far better than taller, more rigid structures built from brick or unreinforced concrete. This earthquake struck along a completely different type of fault than the Cascadia megathrust responsible for the 1700 quake. Haida Gwaii sits along the Queen Charlotte Fault, the boundary where the Pacific Plate grinds sideways against the North American Plate, similar in basic mechanics to the famous San Andreas Fault running through California, rather than the vertical, subducting, motion-driving Cascadia further south. What Haida Gwaii demonstrates clearly is something worth remembering across this entire story. Earthquake size alone never fully determines how destructive an event turns out to be. Distance from population centres, local building practices, and the specific type of fault motion involved all shape the final outcome as much as the raw magnitude number ever could. A magnitude 7.8 earthquake caused remarkably little harm off a remote island chain. A magnitude 9 earthquake striking directly beneath heavily populated coastal cities would tell an entirely different story, regardless of how well those cities happen to be built by the time it finally arrives. Step back far enough from Vancouver Island, past the entire Cascadia subduction zone, past every fault and microplate covered so far in this story, and the full picture finally comes into view. Every earthquake described throughout this entire video belongs to a single, enormous chain of geological activity that circles almost the entire Pacific Ocean. Scientists and the public alike call this chain the Ring of Fire, a rough circle of subduction zones, volcanoes, and earthquake-prone faults stretching from the western coast of North and South America, up through Alaska, across to Japan, down through Southeast Asia, and along the eastern edge of Australia and New Zealand. Roughly 90% of the world's earthquakes strike somewhere along this single connected ring, along with the vast majority of the planet's active volcanoes. The name itself dates back further than most people realize, coined by map makers and geographers long before scientists fully understood plate tectonics, simply by noticing how neatly volcanic activity traced a rough circle around the entire Pacific basin. Modern plate tectonics eventually explained exactly why that circle exists, tracing directly back to subduction zones, just like Cascadia ringing nearly the entire ocean. Canada's stretch of this ring runs directly along the coastline covered throughout this entire story. From the Cascadia subduction zone near Vancouver Island, north past the Nootka Fault, up toward the Queen Charlotte Fault responsible for the Haida Gwaii earthquake, and continuing further still into Alaska. Every fault examined in this story connects, directly or indirectly, into this same enormous planet-spanning system, a reminder that no single fault covered here exists in true isolation from the rest. Being part of the Ring of Fire places Canada's earthquake risk in useful company. The same basic subduction process responsible for Cascadia also produced the devastating 2011 earthquake and tsunami in Japan, along with massive historical earthquakes off the coast of Chile and Alaska. Scientists studying any one of these subduction zones routinely compare notes with researchers studying the others, since the underlying physics driving a subducting plate remains remarkably similar, no matter which stretch of the Pacific Rim you happen to be examining. That shared physics cuts both ways. Lessons learned from Japan's 2011 disaster directly shaped how engineers in the Pacific Northwest design bridges, hospitals, and evacuation routes today. Discoveries made off Vancouver Island, including the tearing fault uncovered at the start of this entire story, add fresh insight researchers elsewhere around the ring can apply to their own, similarly complicated subduction zones. Here is the part worth sitting with. Every headline about a massive earthquake somewhere else around the Pacific in Japan, Chile, Indonesia, or Alaska describes the exact same fundamental process quietly building beneath the waves off Vancouver Island right now. Canada rarely thinks of itself as an earthquake nation in the way Japan or Chile do, yet geologically, this coastline belongs to precisely the same dangerous, restless family of faults circling the entire Pacific Ocean. Zooming out this far reveals just how connected this story really is. Zooming back in, deep beneath the waves off Vancouver Island, reveals something else entirely, a question that has nothing to do with earthquakes on the surface at all, and everything to do with what eventually happens to a slab of ocean floor once it finally disappears for good. Every piece of the Juan de Fuca plate that tears away, drifts off, and stops producing earthquakes has not actually stopped moving. It simply moves somewhere nobody can watch directly, sinking slowly downward into one of the strangest, most extreme environments anywhere on the entire planet. Beneath the crust, the Earth's mantle stretches down thousands of miles, made of rock so hot it behaves less like solid stone and more like extremely thick, slow-moving toffee. Temperatures there climb into the thousands of degrees, and pressure builds high enough to compress ordinary rock into denser, more tightly packed mineral structures nothing on the surface ever experiences. Nothing about this environment resembles anything a person could survive or even directly witness. Every observation scientists make about the deep mantle comes second-hand, pieced together from how earthquake waves bend, slow down, and speed up as they pass through different layers of rock deep inside the planet. A technique closer to listening to an echo than looking at a photograph. A sinking slab of ocean floor entering this environment does not simply vanish on impact. It continues sinking for millions of years, dragged downward by its own weight, slowly heating as it descends deeper into the mantle. Scientists studying seismic waves that pass through the Earth's interior have actually detected the ghostly outlines of old subducted slabs sitting motionless thousands of miles beneath the surface, cooler and denser than the surrounding mantle rock around them, frozen mid-journey on a trip that will ultimately take tens of millions of years to complete. Not every piece of a sinking slab meets the same fate. Some material melts relatively close to the surface, rising back up to fuel the volcanoes running along the Pacific Northwest coastline, the same process responsible for building Mount St. Helens and its neighbouring peaks. Other portions sink far deeper, eventually settling near the boundary between the mantle and the Earth's molten outer core, a layer sitting roughly halfway to the very centre of the planet. Here is where the story turns genuinely strange. Some scientists believe that material sinking this deep can eventually get swept up into massive plumes of superheated rock rising back toward the surface elsewhere on the planet, occasionally fueling volcanic activity thousands of miles away from where that original slab first sank. Material from an ocean floor that existed millions of years ago, in a completely different part of the world, may already be quietly reshaping volcanic activity somewhere else on Earth today, having spent that entire stretch of time slowly cycling through the planet's interior. Even diamonds, formed under exactly the kind of extreme pressure found deep within the mantle, occasionally carry chemical traces linking them back to ancient subducted ocean floor, carried down from the surface, transformed by unimaginable heat and pressure, and eventually pushed back up toward the surface inside violent volcanic eruptions millions of years later. The Juan de Fuca plate tearing apart off the coast of Vancouver Island is not simply ending. It is beginning an entirely new, far longer journey, one stretching across a length of time no single human life could ever witness from beginning to end. Understanding that journey brings this entire story back to where it started, and to the question every scientist covered throughout this video keeps returning to. What is actually happening beneath these waves right now, and how would anyone even know if something changed? Every discovery covered throughout this entire story begins the same way. Scientists noticing something small, patient, and easy to miss, then slowly piecing it together into a much bigger picture. That same patient watching continues today, right now, across dozens of instruments scattered along this coastline, all quietly recording data most people will never think to check. The same GPS stations that quietly track a few inches of coastal creep each year keep recording hour after hour, waiting to catch either a slow bend turning into something sharper, or the sudden release that would mean a major slip has finally begun. Seismometers scattered across the ocean floor and along the coast listen constantly for the faint low-frequency rumble of episodic tremor, a strange, silent kind of slow-motion earthquake happening deep underground that never quite breaks the surface as a felt tremor, yet still reveals exactly how much stress remains locked inside the fault at any given moment. Researchers continue returning to the exact stretch of ocean floor where this story began, off Vancouver Island, checking whether the tearing fault discovered there has grown any quieter or any louder since the last survey. Every new earthquake swarm gets logged, mapped, and compared against decades of historical data, searching for any subtle shift in pattern that might separate ordinary background activity from the first faint signs of something building toward a larger event. Funding fresh research voyages costs a considerable amount of money, and scientists must regularly compete for the resources needed to send another ship back out over this same stretch of ocean. Every additional survey adds one more thin layer to an already detailed picture, sharpening what researchers know while inevitably raising fresh questions nobody had thought to ask before the new data arrived. None of these signals can currently predict the exact day a major earthquake will strike. That kind of precise prediction remains firmly out of reach for earthquake science today, and researchers are honest about that limitation, rather than overselling what their instruments can actually do. What all of this monitoring provides instead is something almost as valuable, a constantly improving, increasingly detailed picture of exactly how this restless stretch of coastline behaves, updated in real time rather than reconstructed years later from old records. That picture keeps changing. The tearing fault uncovered off Vancouver Island transformed how scientists understand this entire subduction zone within the span of a single year. The next discovery, whether it emerges from a future research voyage, a fresh earthquake swarm, or a pattern buried in years of quiet GPS data nobody has fully studied yet, could reshape that understanding all over again. For now, the coastline sits exactly as it has sat for the past 300 years, quiet on the surface, restless underneath. Two enormous tectonic plates remain locked together beneath the waves, storing energy nobody can see and nobody can safely ignore. A newly discovered crack continues tearing slowly through solid rock, a few miles below the seafloor, its final outcome still genuinely unknown, even to the researchers who found it. Somewhere beneath those same waves, right now, while you finish listening to this sentence, the very next signal scientist will spend months studying is already quietly being recorded, waiting for someone to notice it, understand it, and add one more piece to a story that is nowhere close to finished.